and we're going to do 4.4 all at the same time because we are multitasking maniacs. All right, so what we did in section 4.2 was called Riemann sums. Okay, we had a curve, we divided it up into rectangles to estimate the area under the curve. Okay, well, we found that there was all of this area that we didn't take into consideration, or depending upon which sum we used, maybe we were over. Well, if we use more rectangles, okay, then that overage goes down. Okay, so using 4 rectangles, that's pretty good. Using 8, that's going to be great. Using 1,000, oh my gosh, that would be so much better. Using 1,000,000, oh, now we're getting to closer and closer and closer to the actual value of the area under the curve. Well, if we take the limit, okay, now remember this is our area formula right here. That's our height times that base. Okay, so that's the area of our rectangles. Now, if we take the limit as that delta x, as that base gets smaller and smaller, so we have a base on our rectangle like that, well, our base is getting smaller. Our base is getting smaller. Look at this wicked picture drawing. Oh my God, it's amazing. Until finally that base is getting closer and closer to 0. Our rectangle is basically a line which doesn't have any width. So that means we can fill up the entire area under the curve and it will give us exactly that value. So in essence, we're using an infinite number of rectangles. Well, don't panic. We're not going to be figuring out an infinite number of rectangles. We got things to do, my friends. So what we're learning here is that this limit as delta x approaches 0 of all of these rectangles added up is actually called our definite integral. Without the numeric values here, it's an indefinite integral. But with the numeric values, it's definite because you know exactly what that area under the curve is going from. 1 to 9, 7 to 50, whatever. Okay? Now, please don't think that, oh, thank goodness, now that we know definite integrals, we're never, ever going to use Riemann sums again. Oh, that's just not true. Sometimes we won't have an equation to deal with. We'll only have data, and we'll need to estimate that area under the curve. Still, we'll need Riemann sums. All right, so our definite integral here means we're going to find the area under the function to the x-axis going from a to b. So if we draw a little picture, okay, we've got our function from a to b. That integral is going to find this entire area. The whole entire thing, it's going to cover it, no estimation, it's going to be exact. Now it's only going to take that area to the x-axis. So if its area is above the x-axis, we're going to count that as positive. If the area is below the axis, we're going to count that as negative. Okay, so we might have something that looks like this. Okay, if we're going from A to B, this area up here is going to be positive, this area is going to be negative. So you can see the area below the curve is bigger, so our answer may be negative. Now there are a couple theorems in calculus that are pretty important. This is one of them. Now this is called the first fundamental theorem of calculus. There should be an echo machine behind me because the first fundamental theorem of calculus is very important. That's why they call it fundamental, and it's the first. Okay, so gots to remember this one. Okay, so what is it that we do when we have a definite integral? Well, we're going to integrate it just like we did in section 4.1. And then we're going to plug these values into that new and improved function. So once we integrate it, we're going to plug b in for all the x's minus, then we're going to plug a in for all of the x's. Okay? Now, an indefinite integral has a plus c. but a definite integral does not. And that's because the c cancels out. Really what we had was f of b plus c and then minus f of a plus c. So those c's would cancel each other out. And what we end up with is a numeric value, because remember, this is estimating the area under the curve. So that will be a numeric value. Okay. Now, another theorem that we should know is that continuity implies, and I can't say that word, integrability. Blah, it's a mouthful. So if you're continuous, you will be able to find that definite integral. And that makes sense, because as long as you have a nice smooth curve, you're continuous, you will be able to find that area under the curve. Okay? If you have a break or a hole or vertical asymptote, you're going to have trouble finding the area of the curve once you get to that hole, break, or vertical asymptote. Okay, so now to test our abilities here. If f is defined at x equals a, and we take the integral from a to a, remember that first fundamental theorem of calculus, you're going to integrate, you're going to plug the top endpoint in, minus, and then you're going to plug the bottom endpoint. So if they're the same number, that's going to give you 0. And that makes sense because you're finding the area under a curve at just a point. There's no interval range there, so that would be 0. Now, we can switch these values. So if we have a to b, we can switch then b to a. Think about what that would do to our answer. Okay, that's going to be the opposite, because this is going to give us f of b minus f of a. This is going to give us f of a minus f of b. They're just opposites of each other. Now this one's kind of nice. You've got that point in between. So it's kind of like saying we're finding the area from 1 to 7. Well, that's going to be the same as the area from 1 to 3. And adding that from 3 to 7. You're just taking a little break in between. The key to this little property here is the fact that whatever this number is, that's what this number has to be as well, so that they butt seamlessly up together. Well, let's give it a whirl, Pearl, and see what we get. Okay, so we're going to integrate first, and then we're going to plug in the top limit, and then we're going to plug in the bottom limit. Okay, so if we integrate x to the second, we're going to get x to the third divided by 3, and then we change our notation. We put this little skinny bracket, we put a little 3 and a little 1 there. 3 is that top limit, 1 is that bottom limit. We're always going to plug in the top limit first, subtract the bottom limit. Okay, and then we're going to find out exactly what that value equals. Well, 3 to the third power is 27, so 27 thirds minus 1/3 is 26 thirds. So that represents the area under the curve to the x-axis. It's positive, so we know that area is above the x-axis. Okay, so same thing here. We're going to integrate sine, which is negative cosine. We're going to plug the pi in first and then the 0. So negative cosine of pi minus a negative cosine of 0. Please be careful. This is something you should know how to find without the use of a calculator. So we've got the cosine of pi. Well, the cosine of pi is -1, but you're taking the opposite of that, so it's +1. Minus a minus, so that's plus. Cosine of 0 is 1. So we end up with 2 for our final answer. Now, even though we've got cosine, negative cosine of x is what we're using and plugging these numbers in, you are finding the area under the curve of sine. Okay, so you're finding the area under the original function. Okay, let's do another. Now, cosine, the integral of cosine is sine Gosh, I hope if I ever switch and accidentally say derivative, please know we're talking about the integral. There's 1,000 different words, and boy, you really get tongue-tied. So cosine, the integral of that is the sine. We're going to take that from 2 pi to 0. So I'm going to have the sine of 2 pi minus the sine of 0. Well, the sine of 2 pi is 0. The sine of 0 is 0. I get 0. Huh. That's kind of weird. Well, not really so weird if you think about your graph of sine. Sine starts at 0, goes up to 1, the top of its amplitude, 0, down, 0. So you've got exactly the same amount of area above the curve as you do below the curve. So they cancel each other out. Now, the bigger the function, the more exciting it gets. Ooh, this kind of got lost, but it's on your worksheet, so you're following along. When I integrate 3x to the third over 3 plus 5x squared over 2 minus 4x, I'm going to go from 3 to 1. You will want to simplify as much as you possibly can. So for instance, these 3's, I would cancel them out. I would even rewrite it so it looks nice. So when I do that, that's going to be 27 plus 45 over 2 minus 12 minus, then you're going to plug the 1 in, 1 plus 5 halves minus 4. Make sure that you're distributing that negative through, so your final answer should be 38. Okay. Now they like to do things so that you can use, so that you don't have to use your calculator, and it makes things a little bit more fun. And it's basically showing that you know those properties. So for instance, they're not going to tell us what f of x is. So there's no way we can integrate it and put in these values. We just got to go on our properties and hope we know the answer. So they tell us that from 2 to 6, we know that f of x, the integral is 2. So the area under the curve from 2 to 6 is 2. The area under the curve from 6 to 8 is 5. So let's see if we can figure out what these guys are equal to. Okay, so they want us to go from 2 to 2. Well, if we go from 2 to 2, this value is the same as this value. We know that that answer is 0. Okay. 8, I'm going to split that up. 2 to 6, because I know the value of 2 to 6. Plus, from 6 to 8, I know that value. And then I can add those together. So from 2 to 6, the area under the curve is 2. From 6 to 8, the area under the curve is 5. So that total has got to be 7. Okay. Now this one on number 9, we're going from 6 to 8, but we're taking 5 times that. Remember that you can pull that constant, that coefficient rather, through the integral. So this much of it is 5. You're going to multiply it by 5, so my final answer is 25. So your first fundamental theorem of calculus. Now we're going to skip over a little section and we're going to move to the second fundamental theorem of calculus, because once we're fundamental Lazen, we might as well go ahead and just do them all together at the same time. So we're going to move to the second fundamental theorem of calculus. The second fundamental theorem of calculus states that when you're taking the derivative of an integral of a derivative or of a function, these guys are going to cancel each other out. Now, if we were working with just a plain, ordinary, indefinite integral, we wouldn't have any problems whatsoever. But the fact that we're working with a definite integral, we've got values coming through here, we've got a little bit of a problem. So, that first fundamental theorem of calculus, what's going to happen is when you take, and I don't know if you thought maybe that was a typo or not, but it isn't. When you're looking at this, let's do red. Okay, we started off with a function with t's in it, but because we're integrating this from x to a, and x is a variable, notice we've got that little x out there. When we integrate it, we're going to be putting those x's in. So when we go back and differentiate it, we're going to have a function that has x's. And let me show you what that looks like. Okay, they want us to find the derivative. So the first thing we're going to do is take the integral. So I'm going to integrate this. So that's going to be t to the second over 2 plus 2t, and I'm going to put x's in and zeros in. So that's going to give me x to the second over 2 plus 2x minus, when I put zeros in, I get zeros. So that's just x to the second over 2 minus 2x. Well, now they want me to take the derivative of this. Well, when I take the derivative, that 2 is going to come down in front, and I'll have just plain x minus the derivative of 2x, which is 2. Oops, somewhere I lost my plus sign there. Oops, this was a plus, so that's a plus. Okay, so I have x plus 2. So I end up with exactly the same thing, only now I have x's. Well, what's nice about that is knowing this formula. This is a constant, and this is a variable. When I integrate, then differentiate, I'm going to end up with that function with all x's inside. Okay, so knowing this, I don't have to integrate this because some of the integration could be quite tricky. All you're looking for is that an x and is that a 1 or any other constant. If that's the case, when you integrate, it's going to get bigger, differentiate, it's going to come right back. You're going to have all x's where the t's were. Okay, so number 15, what's that going to look like when you take the derivative? It's going to be x sine of x. This one, it doesn't matter what that constant is because whatever that constant is, you would have a number and the derivative of a number is 0. So this one, once again, you're just plugging in that x. Okay, now the more intense form of the second fundamental theorem of calculus. You knew it couldn't be that easy. Now what's going to happen is what we have up here maybe isn't just an x. Maybe it's a function involving x. Like in our example here, we have 3x. Okay, this still has to be a constant. It has to be a pure number. Okay, now what's going to happen is when we integrate this, we've got t squared over 2. When we integrate this, we're going to be slipping that 3x in there. So now we've created a chain rule. Let me see if I can rewrite that. Oops, there we go. So it's a whole function, so you're putting that whole function in for all the x's. You've created a chain rule. So now when you take the derivative, you need to make sure that you're bringing that 2 down in front, subtracting 1 from the exponent, which looks like this guy, and then you're multiplying by the derivative of what's inside, which is this guy. Okay, so what we end up with is putting in the 3x for all the t's and then multiplying by the derivative of that exponent. So what we end up with is actually our 3 times x times 3. Okay. All right, so let's look at another example, which by the way is 9x. Okay. All right, so the same thing. We are going to put in our x squared for all of our t's. So that'll be 1 over x squared to the 3rd. And then we're going to multiply by our derivative of x squared, which is 2x. And then, of course, we are always going to simplify this. This is 1 over x to the 6th times 2 over x, which is going to simplify to 2 over x to the 5th. You're taking the integral, which makes it bigger, and you're plugging in a function, which makes it a chain rule when you take the derivative back. Okay? So on number 18, same thing. We're going to put 4x in for all of the t's. And then we're going to multiply by the derivative of 4x, which is 4. Okay? As long as what's on top is a function of x and what's on the bottom is a constant, we're perfectly okay. So Number 19, we are finding the derivative, and I apologize for not writing that down because we do not want to get confused as to what this guy is. Okay, we're going to put cosine in for all of the t's. Then we're going to multiply by the derivative of cosine. Remember, the derivative of cosine is negative sine. And you can rewrite that using other notation, your squared notation like that. Okay, now on number 20, ooh, that's a little tricky. We've got a variable on the bottom, we've got a variable on the top. I'd like you to see if you can figure out what you might want to do or what you could do with that. Okay, and I will see you back in class and we'll discuss this in person.